Hi folks, Mr. Ackerman here. Thanks for watching. Topic of today's video is electric fields, and what we're going to be talking about today is something that you're actually familiar with, although you're familiar with it in the sense of gravitational fields. If you can make the connection between the terms that we're going to be using here as they apply to the electric force and the similar terms that we used when we talked about the gravitational force, I think you'll see that this is actually not too difficult to comprehend. So take a moment to pause the video and have a look at the questions we're going to address, as well as where we are in the unit schedule and the learning goals and success criteria, and then rejoin us. Okay, you're back, and here we go. Let's get started. First of all, what do we mean when we say electric field? Well, first of all, if you can compare it to what is called a gravitational field, like I said, I think you're going to have an easier time understanding what we mean. So we're going to start off by talking about a single point charge and asking ourselves what is meant by the term electric field. So as a simple matter, let's talk about, let's say, a positive point charge, which I'm going to signify like this. Now, if we're wondering what is the electric field, well, we know a little bit about this. For example, we've already learned that a force field is a region around some object where forces are being exerted. In the case of gravity, that object is usually a planet. It's the one you're most familiar with. And because gravity is such a weak force, you actually need the mass of something really huge, like a planet, in order to really feel the effects of gravity. I mean, you don't feel the force of gravity between you and your house, even though the house is pretty heavy. It's just not massive enough. Gravity is the weakest of the fundamental forces. But think about something charged like an electron, or since I've drawn a positive charge here, think of something like a proton. Or for that matter, think of a balloon that you've rubbed in your hair and that has become charged. The electric field is quite noticeable in that case. I mean, the balloon rubbed in your hair can easily make your hair stand on end. It could pick up small pieces of paper. It could stick to the wall. So the region of force around that is very easy to imagine once we realize what we're talking about. And to make it into a diagram, we're going to stop talking about electricity for a moment and instead talk about mass, and let's say something like the planet Earth. If you had the planet Earth here, and I've designated that with the letter big M, and I asked you what is the gravitational field, remember a couple lectures back we learned that you would try to answer the question, how are objects near this planet being affected by the force of gravity? And the answer is that they are being pulled inward down toward the center, as indicated by these lines that I'm drawing, these force vectors. They go all around the mass. They point radially inward, so inward along a radius, and the farther away you get, the shorter they get. They start getting more and more spaced apart, and this signifies that the gravitational field way out here is weaker than it is when you're close. So I could draw something like this with ever decreasing lines, just like that. This would be a map, if you will, of the gravitational field. It gives me an idea of the shape and the direction. Well, in a similar way, we can talk about the electric field. We have a positive charge here, and so now the question becomes as follows. How will another charge be forced if it comes near this charge that I've drawn? In other words, what forces will it feel? However, we've got a little bit of a problem here. There are two kinds of charges, remember. There's positive and negative charge. We did not have this problem with gravity. There is no such thing as negative mass. Gravity is always attractive. So I have to specify what kind of charge I'm dealing with. Now, to give me a little bit more space, let me just pull this down a little bit. Oops. There we go. Let's suppose, for whatever reason, you decided, I'm going to talk about positive charges. Okay, so now imagine this. How would a positive charge that was brought near this other positive charge here, how would it feel? Well, it would be forced away, of course. That's the law of electric charges. There would be repulsion. If I put the charge here, it would feel repulsion this way. and so on and so forth. So what I can actually do is start drawing some lines that go outward like this, and they would go all around this black charge that I've drawn. Maybe you want to call this the central charge here. Okay. If I were to place this positive charge a little bit further out, what would I notice happening? Well, now it would still be forced away, but the vector would be shorter. So I'm going to draw this. And I could go on all day drawing this. It's kind of fun for a little bit, but then it gets kind of tedious. The idea, though, is that we are now mapping the electric field by asking the question, how will another charge be forced if it comes near the central charge? Now, this essentially is what we mean by the term electric field. These are the electric field lines, as they're called, and they show you the lines of force. It compares very, very well to a gravitational field, except that in this case it points outwards. Of course, you may say, hey, why did you pick a positive charge here? Why didn't you pick a negative charge? Would things have changed if I had asked the question, how would a negative charge be forced around this object here? Well, let's see what would have happened. Let's draw a positive charge there, and now let's take a negative charge and place it in different regions around here. For example, like this. This time it's going to be attracted. And in fact, if you put it here, it's going to be attracted like that, and then like this, and so on, and so forth. In fact, the only thing that really changes is the direction of these lines. The magnitudes don't really change. The idea is still the same. However, we're about to run into some confusion, because how do we know if we're calling up our homework partner to figure out how to do a problem, how do we know that he or she is using the same rule that we are? Like, how do we know when we're talking about electric field, which of these two charges the other person's talking about? Well, by agreement among all physicists worldwide, we always talk about the positive charge. So what you're going to hear me mention a number of times in this unit is the concept of a unit positive test charge. Whenever we are dealing with electric field, or for that matter, other concepts that we're going to learn, we're going to think of a positive test charge. And you might wonder, how much? How much charge should that be? Well, if you remember, when we deal with electric field in gravity, we're talking about the letter G, which on the surface of Earth, you recall, is 9.8. The units are newtons of force per kilogram per 1 kilogram of stuff. Well, in the same way, when we talk about electric field, this charge, which is being used to test out the electric field, is going to be a unit. Unit means 1. Positive test charge, and of course charge is measured in coulombs. So you're going to hear me say the words +1 coulomb test charge a lot in this unit, and this is what I mean. It's our way of keeping everything consistent between all the people we talk to when we're studying this. So in other words, going back up here, which of these pictures is correct? It's the red one, because the red one was drawn using a positive test charge at various locations around the central charge. The blue one, as pretty as it looks, unfortunately, would be too confusing. We don't use that one. This would be a negative test charge. We can't have that. Okay, so this is what we mean by electric field, and obviously there is a relation to the gravitational field. And that brings up the idea of, well, is there an equation to calculate this? So let's go to our next slide. We're going to talk now about the actual intensity or strength. In other words, how many newtons of force are experienced per coulomb of positive test charge. That's the question we're going to be answering. In a similar way, when we talked about gravity, it was how many newtons of force per 1 kilogram? That's the question we answered in gravity. Of course, there was no such thing as positive or negative kilograms, so we didn't have to worry about this. But with electric charges, we do. So what did we do with gravity? I think if we think about what we did with gravity, we'll quickly see what we do with electricity. Remember, with gravity, the force formula for the magnitude is G, big M, little m, over the distance squared. That was the force, and the field strength, or intensity, became little g equals big G, big M over r squared. Go back a few videos to find out where this came from. Well, in the same way, our formula for electric force is K, big Q, little q, over r squared. And so therefore, since the mathematics is the same, the electric field, which is given the letter fancy E or script E, is going to be K, big Q, over r squared. So isn't it nice? I just saved you having to learn a whole bunch of new stuff by just making a comparison here. We don't have to go through all of the derivations here. Just like we had for gravity, we have for electricity. Just like in gravity, this was the mass at the center, for example, a planet, and it showed up here as well. This will be the charge, if you wish to think of it this way, at the center. So going back, what you would do is plug in this charge as the Q. The other Q is 1 coulomb, remember, a unit test charge. And you would go around at different points and try to figure out how many newtons of force is that 1 unit of charge feeling. So as an example, let's try one. Suppose you found yourself 0.5 meters to the right of a +3 NC. What does N mean? Again, if you don't know your metric prefixes, you're in a little bit of trouble in this unit. This is nano, 10 to the negative 9 coulombs. If you don't know them, in fact, pause this video now and go memorize them once and for all. You cannot continue in science without knowing these off by heart. You don't want to embarrass yourself. 0.5 meters to the right of a +3 nanocoulomb charge. And what we're going to do is find E, the electric field. Now keep in mind, electric field, just like gravitational field, is a vector. So these formulas give the magnitude. It's your job to use the law of electric charges to find the direction. So what would we do here? Well, let's draw it out. Here is +3 nanocoulombs as the central charge. And we're going to be 0.5 meters to the right at this point. So I could draw that in as 0.5 meters. Remember, it's from the center here to this point here. And we want to ask ourselves the question that we asked before: what is the force direction on a +1 coulomb test charge there? So let's try to imagine +1 coulombs here. What direction will be the force acting on it? I think you know by the law of electric charges it will be to the right. And therefore, this is the direction of the electric field. All that's left to do is to find its magnitude. So we're going to use this formula to calculate that. K is 9 times 10 to the 9. Q is 3 times 10 to the negative 9, that's nano. And we have to divide by 0.5, and don't forget to square. So what do we get when we do that? Well, this is fairly easy to do without a calculator. 9 and 10 to the negative 9 are going to give you 1 when they multiply. The 9 and the 3 there are going to give you 27. And that's all over 0.5 times 0.5, which is 0.25. So that's like having a factor of 4. 4 times 27, I believe, is 108. and that will be the number of newtons per coulomb of charge. But since I know it's directed to the right, then in my final answer, I'm going to do this. 108 newtons per coulomb to the right. That means if I get 1 coulomb of charge, it'll feel 108 newtons. If I get 2 newtons of charge, it'll feel 216 newtons. In other words, what I'm trying to say here in the end is that just like you had up here as one more step, Fg equals mg, guess what? For electric force, you'll have now Fe equals Q times E. This force is the force you can calculate if you know what E is at a certain location. Just like this force is a force you can calculate if you know what G is at a certain location. We use this formula when we're on the surface of Earth, and we know that G is constant 9.8. So we can use this formula to calculate force if we know E at a certain location, for example here, and we decide how much charge is going to be there. So what I might ask you as a second part to this question is the following. Just give us a bit of space there. Here we go. Let's call that was part A. So now part B. What force will a -3 millicoulomb charge experience at that same point? Okay, so now you have to imagine -3 millicoulombs being placed right here. So I've thrown you a little bit of a curveball here. Can you guess what the curve is? Take a moment and see. All right, and you're back. Here, when we calculated the electric field, we had to imagine the +1 coulomb test charge, so we got a direction to the right. But now I've said, imagine that a charge of -3 actually goes there. What's going to happen to the -3? It's going to feel attraction. So actually here, we're going to get that the electric force, which is Q times E, is equal to -3, milli means 10 to the -3, times 108 newtons per coulomb. That was to the right for positive charges, but because I now want to reverse the direction because I'm dealing with a negative, now I insert a negative sign here to remind me of that. What is 3 times 108? I believe it's 324. It'll be -324 newtons right, or we could call it positive 324 newtons to the left. All right, so did we really learn anything new here? Not really. If you knew how to do this stuff with gravity, then just switch the letter big M for big Q and proceed as before, keeping in mind the idea of positive test charges and the law of electric charges. All right, let's move on. There's a great FET simulation that I want you to check out, and it's going to help us get into some more complicated charge configurations. See, here's the idea. Go to FET and go under Physics, go under Electricity, Magnets and Circuits, and find Charges and Fields. Download it, and you're going to get something like this. All right? Here's the idea here. When we're talking about gravity, we are often talking about one object, like a planet or a moon, something like that, maybe a star. In astronomy, in many situations, there's only one object of importance that is in the vicinity or in the area that we're talking about. Of course, sometimes you'll talk about large collections of objects, like in a star cluster or in a galaxy, or maybe in a really crowded solar system. However, quite often, it's just one object. Well, that's not the case very often with electric charges. See, matter is made up of countless electric charges, and therefore, there can be large charge distributions. For example, think of a water molecule. You know that there are two oxygen atoms and one hydrogen atom, or sorry, two hydrogen atoms and one oxygen atom. That means there are at least 3 areas of the molecule where charge can accumulate. If you're a chemistry student, you know that the oxygen atom develops a slight negative charge and the hydrogen atoms develop slight positive charges. We've now got three charges interacting to form an electric field. What does the overall electric field of the water molecule look like? Well, in the FET simulation here, you can play around with that. For example, you could take oxygen and represent it as this positive charge here. Sorry, that would be the hydrogen I'm talking about. Hydrogen there. You can drag another hydrogen over here, and you can drag, for example, oxygen up there, and look at the shape that you get. Just going to move this into high res here. Look at the shape that you get for the electric field. It's pretty confusing until you know what you're talking about with electric fields. So let me show you how to use this. Let's start simple. The first thing we're going to do is look at not the electric field due to one charge like we did back here, but now we're going to look at the electric field due to two positive charges. So what you can do in the FET simulation, take a positive charge and place it on two of the lines that cross here on the grid. And what do you see? You see a very dense area of electric field lines getting less and less dense as they move out. This is just the outward electric field that we talked about when we looked at this. Sorry. When we looked at this, right? This is nothing new. It just looks a bit different on the FET simulation. Now imagine I take another positive charge and I move it over here. What do you think is going to happen? Before I drop this charge in there, see if you can predict what's going to happen by maybe pausing the video and doing a little sketch on your own. Okay, and you're back, and now I'm going to drop the charge in. There it is, and look what happens. Looks like a big mess. Let me get out of high res here. Let's start simple. What do you notice? All around this charge, the arrows, the force vectors are pointing outward, and all around this charge, the same thing is happening. But at some point, the arrows start going up like that or down like that. Why is that happening? Well, to figure this out, let's go back into this program here and do a little bit of sketching. Think about the positive test charge that we talked about. The idea for mapping out an electric field is to imagine a positive test charge located somewhere near any collection of charges and to ask yourself, what force would it feel? Since this central charge is positive and the test charge is positive, there's going to be a repulsion away from this charge. At the same time, there will be a repulsion away from this charge. These are force vectors, so we add them using vector addition, and what do you get? Maybe I'll use a different color here. You get these two adding to an upward net force. In fact, the same sort of thing starts to happen down below. If I place the positive test charge here, I'm going to get repulsion and repulsion, and those two are going to add up. The horizontal components will cancel, the vertical components will add, and I'll get this. Let's go back to FET and see if that's indeed what we see. Yeah, in between the two charges on the line that bisects this, that bisects the line joining them, we see an upward direction to those force vectors and then downward over here. Let's try a region that is maybe over here. What would you get if you placed your test charge here? If you place your test charge here, here's what's going to happen. There will be repulsion from this charge going in that direction, but there will also be repulsion from this charge, and it'll be stronger than the repulsion from the other one because we are closer. So you might draw this. Now you'd have to add these two vectors to get the vector sum. What is the vector sum of those two vectors? It's something like this. So I should notice that the vectors in this area point up and to the right, but more up than right. Let's see. Sure enough, they do. They all go up and to the right. Now you repeat this process all around and you map out the shape of the electric field. What do you get? Well, if you, let me just delete some of these if I can. If you do this enough times, the shape that you're going to start to get, sorry I wasn't able to delete that, my deleting only goes back about 20 steps, but that's okay, because let's watch what happens. Watch these lines. They're kind of going like this. And this is what we call the electric field due to two positive point charges. It points outward. You notice that the lines from each charge, they start to repel one another. They never cross, because if they crossed, that would indicate two net forces at one point in the electric field, and this is impossible. And so there you go. This is a lot more confusing than just a single point charge. And that's why electric charges can be a little more confusing than masses in gravitational fields. I'm going to leave it to you to repeat this for two negative point charges. So go back to FET, click Clear, and now drag negative charges in and play around with the simulation, right? And then repeat with two opposite point charges. So do a negative and a positive and see what you get. First, predict the shape by sketching as best you can, and then see if it confirms what you predicted. All right, moving on. Let's do a calculation now for 2 point charges, just so you know how to do the mathematics. So right now what I'd like you to think of is, let's imagine a positive charge over here. Or, sorry, let's make that one negative like we did in FET. Blue is negative. Red will be positive. To keep things simple, let's make this plus 1 nanocoulomb, and let's make the blue minus 1 nanocoulomb. Let's separate these guys by 1 meter. I'm going to try to use the number 1 as much as I can to make the math a little bit easier. And I'm going to ask you this. If this is the line joining the centers of the two charges, what is the electric field? How about right up here? If this distance here is also 1 meter. So on the line directly above the positive charge, and therefore up and to the right from the negative charge, what is the electric field? So let's write that in there, right in the question. Calculate the E field here. So what are we going to do first? Well, the first thing we're going to do is we're going to imagine a +1 Coulomb test charge at this point. So let me put that in, positive, to remind you that something positive has been placed here. Let's give ourselves a bit more room. What are we going to do? Well, a negative charge sitting over here is going to attract a positive charge there. A positive charge here will repel that charge there. Because these two have the same charge, they're both 1 nanocoulomb, a billionth of a coulomb, therefore the closer charge will have more influence. So there will be more repulsion than the farther away charge. So let's try to draw that in. I want to show a lot of repulsion, but I want to show a little bit of attraction. So I hope you can see that the red force vector is a little bit longer than the blue one. And now I can number these. If this is charge number 1 and the red one is charge number 2, then I can call this the electric field due to 2, and I can call this one the electric field due to 1. The idea is to use force vector addition, so components, to add these two and get the net electric field. How do we calculate each of these? Easy. Use your formula that you developed back here, kq over r squared. So this will be kq1 over r squared, and you're going to need to find that distance. It looks like we have a right angle triangle with sides of 1, so I think that's going to be a root 2. The blue r is going to be root 2 meters, if you want to do a Pythagorean theorem. And we can do the same for this one. This will be KQ2 over R, the red R squared. This time, the red R will just be 1 meter. I made that easy for you. All right. And then what you're going to do is you're going to figure out what is the vector sum of these two. So E1 equals something, comma, something, plus E2 equals something, comma, something. And then you're going to add these up, and you're going to get E total equal to something, comma, something. Don't forget to find the magnitude and the direction, like that. And also don't forget, maybe you want to do something like this, positive y direction up, positive x direction to the right. You're going to need to do some trig to find an angle in here. So how would that look? I don't think that's too hard. You can probably find an angle theta in there. I think you can use SOHCAHTOA to get that angle. In fact, I think it's going to be 45 degrees, no? Because you have 1 meter here and 1 meter there, right? So this shouldn't be too hard for you. Keep your positives and negatives in line with one another. Fill in these numbers. Fill in an x1 and a y1. Fill in an x2 and a y2. Add them up and get the final xy combination. Magnitude with Pythagorean theorem. Direction using trig. And you should be able to find the electric field there. I'll just pause the video for a second and I'll do it quickly myself so that you have an answer to work. Okay, folks, and I've done the calculation here. I can fill you in on some of the details, but I don't want to do too much of it for you. Got to leave you a little bit of torture there, right? E1 comes out to, or E1 plus E2. What I got down here is for this component, I got negative 3.18 and some extra digits, and for the y value, I got 5.818 and some extra digits, so that when I found the magnitude of these, I got 6.63 newtons per coulomb, and when I got the direction, that ended up being up about 29 degrees to the left. Okay, so something like in that direction. What you're going to end up with is an electric field overall being something like this, which means that any object which is in this area, right over here, is, if it is positively charged, will be forced that way, and if it's negatively charged, it will be forced down this way. All right? So just to wrap up, let's take a look at a really interesting charge distribution. Instead of just looking at two charges and what their electric field is, we're going to look at an application that's actually quite important, especially as it applies to any device that stores electric charge, such as a capacitor is actually what it's called. These are devices where you can store electric charge to be used very quickly as needed. An example that you're all familiar with would be a flash on a camera. A flash on a camera gets charged by the battery in the camera, and then it releases that energy very, very rapidly to produce a very bright pulse of light. So the way we do this is we take two conducting metal plates, and these should be very, very large plates, and we separate them by a certain distance. And then what we do is we place equal amounts of charge on each, but they have to be opposite charge. So for example, you might, I suppose you could do it this way, you could rub a balloon in your hair so that the balloon became negatively charged, and you could touch the balloon onto the upper plate, let's say. Negative charge from the balloon would jump onto the plate. Because it's a conductor, those charges will spread out. They will repel one another, and the conductor nature of a metal plate will allow it to spread out evenly. Now we want to put the exact same amount of positive charge on the bottom plate. So I suppose since the balloon would be negatively charged by a certain amount and your hair would be positively charged by the same quantity, I suppose we could touch the bottom metal plate to your hair until the same amount of charge was deposited. Of course, I don't think physicists really do it this way. They have other ways of charging plates, but you get the idea. Now, we're going to ask ourselves, with so many charges spread all over the place, what is the electric field in here? Do we have to do this kind of calculation with not just two charges like this, but with many, many, many charges? I mean, really with like countless thousands and millions and billions and trillions of charges? Well, we do technically, but there are mathematical ways to deal with this. It's called calculus, which you're going to learn next year in first year university. However, for now, let me use a little bit of a qualitative argument to give you an idea of what the electric field is like in between these two oppositely charged conducting parallel plates. Let's take our good friend, the positive test charge, and place it right in the middle. +1 Coulomb test charge. What do you think the force exerted on it will be? Well, positive charges get attracted to negative ones, so this charge here will feel attraction to every single charge on the upper plate. The angle will be different for each force vector. However, another thing to notice is that for the charges that are really far away, the force vectors will be short. For the charges that are close, the force vectors will be long. Now, what else do we know? The positive charges at the bottom are repelling this. And in fact, if the charges are equal, like I said, equal charge on each plate, we have just as much attraction to the top as we have repulsion from the bottom. So I can basically just go over these with more force vectors. In the end, do you see what's happening? I hope you can see that the horizontal components will cancel and the vertical components will add. In the end, you will get a net force vector pointing upward like this. And in fact, if you go, let's say, a little bit closer to this side here, will things change? Well, yes, they will, but no, they won't. Let me show you what I mean. You'll be much closer to the bottom plate, so the repulsion will be much stronger than before. It'll be like this. I should draw that a lot longer. Be like that, like that, like that, like that, and so on. The attraction to the top will still be there, but it's going to be less because we're farther away. So this time I'll draw shorter vectors. First of all, quick observation, the same thing about the horizontal components happens. The horizontal components cancel. All that's left is the vertical. But I hope I can convince you without doing any math that while we are farther from the upper plate and therefore there's less attraction to it, we are closer to the bottom plate, so there's more repulsion. As it turns out, the effect cancels and you end up with the same amount of force you had in the middle. So I can draw another electric field line straight up, the same magnitude as the one from the middle. And for that matter, if we put a positive charge over here, we end up with the same thing. We are now going to get a lot of attraction to the upper plate, more than in the middle, but less repulsion from the bottom plate. Horizontal components canceling, net result, still an electric field line pointing this way. Do this, repeat this in every imaginable location in between these parallel plates and try to catalog the results. Now you can do this on your own in your spare time, or we can sneak a peek. We're going to cheat a little bit here. Take a look at a picture that's out of your book. The book is Physics 12 by Nelson. This is a photograph of two oppositely charged metal parallel plates which are surrounded by a mixture of oil and rayon fibers. These are clothing fibers. And the fibers charge up, they get polarized, and they line up in the direction of the electric field. What do you notice about this electric field? I hope you can see that first of all, it is very uniform. It's almost like, think of G equals 9.8 on our surface, the surface of Earth. It doesn't really matter if you go to the top of the building, the bottom of the building, Toronto, Montreal, Vancouver, wherever, you pretty much have 9.8 newtons per kilogram down. Well, in here, you have a certain number of newtons per coulomb, the direction, in the direction of these lines, from the positive plate to the negative plate. One thing that is hard to see in my diagram because I haven't drawn it fully yet, but you can see it here, is near the edges of the plate we don't have a uniform field. Here we have some bulging. We call these the edge effects, but if we stay near the middle, the electric field is uniform. And what you're going to see later on in this chapter is that we can exploit this to build technologies that harness the power of electric charges that are moving through these electric fields. And that's where we're going to leave it for today. There's a little bit more in your textbook to learn about, and I'll leave it to you to discover that during the reading. But for now, I hope you have an idea of what we mean by electric fields, similar to gravitational, but different in that there can be many more configurations that you're likely to deal with, and therefore you have to learn how to deal with those test charges. All right? Anyway, thanks for watching, and oh, I realize I forgot to do the fact of the video. We can't have that. What was my fact of the video? I have to find it here. Here it is. The fact of the video is simply these two equations. The new formula for the electric field due to a single point charge, and the new formula for the electric force if you know the electric field. So let's write that in now as the fact. Make sure you're ready in class tomorrow, and I will see you in class. Take care now.